How does the soldier of today become the soldier of tomorrow?
You see technologies now progressing to the point where it makes sense to put an exoskeleton on the battlefield.
Imagine if we could replace all the small arms projectiles with one. If a soldier has a rifle, he has the same capability as an M1 Abrams tank.
Cloaking is essentially invisibility. I think you can think of many possibilities where you're out in the battlefield and you'd like to not be seen.
Making warfighters and their gear lighter, stronger, and safer with more firepower. Ensuring America's future soldier is a decisive weapon.
There are so many tasks within the Army that we ask soldiers to do every day that are heavy lift tasks, that are sustainment, that are long-term marches. And if we can provide something that makes what they do every day easier or allow them to do it for a longer period of time without physically getting exhausted, it helps them on the battlefield. Whether it's advanced sensors, whether it's running faster, to be able to carry a heavier load for a longer distance, a device that knows you, that can learn you, and if it needed to, it knows how you walk, so maybe it takes you back. There's so much potential, I think, when you provide a frame like that or some type of device for personal augmentation.
One of the issues we've been looking at to distribute the load effectively or to help the soldiers carry load is the idea of the wearable robots or the exoskeletons. We looked at the full body exoskeleton as well as just strictly a lower body, where the lower body is just carrying the backpack load, and a full body has the ability to either do that or carry a manual load carriage in the arms. At this point, the engineering has demonstrated that it can work. So the next question is, as physiologists and biomechanists come together with engineers, the question is how well will it work? If soldiers are expected to carry 120 pounds and walk at 3 miles an hour in the field, we're certainly going to evaluate it to that degree in the lab. And one of the things that we've gotten smarter with over the years is that you can't just take a novel piece of equipment and expect someone to wear it. So as we get smarter in our research protocols, we've been building in more and more learning time, familiarization. It's an interesting feedback that we get. Some of the soldiers felt like they were more used to carrying the backpack by itself without the device because that's what they're used to, whereas other volunteers felt like they'd rather feel the effects of the device than rather have to feel the effects of the load on their shoulders. We've tested 2 prior versions, and each time we're seeing incremental improvements in how well it works. Our long-range research plan is to be able to address things in a very isolated environment here in the lab, and then to grow that research out and start getting into the field more.
You have to enhance the soldier's strength to enable him or her to carry what they need to carry, giving him a better fit to the equipment that we have and actually designing and building equipment around his needs. The exoskeleton is an option that we have. It can provide considerable strength to carry things. One of the disadvantages is cost. And the question is the maintenance. The question is who would be wearing the exoskeleton and on what missions.
While soldiers need strength and endurance on the battlefield, there are times when they also need stealth. Camouflaged uniforms can help soldiers move undetected when the mission calls for it. In the future, a revolutionary new technology might even make the soldier invisible.
If I were to make myself invisible to you, what I would do is I'd get a cloak. And the cloak would consist of a cylinder that I would put around me. What would happen is the light coming from the wall back there would hit the back of the cloak, come around, and then go right to you. So you would see basically right through me. With metamaterials and the new kinds of materials that we are developing, we are able to control light as never before. It's like a whole new ball game. You start with some sort of given material like silicon, let's say, or something like that, and then you embed it. You embed it with small nanoparticles or tiny gold rods or maybe even tiny slivers of semiconductors. Now, by making these metamaterials, we're able to control light in these new ways. All the textbook things you read about light are now wrong. We can do things that beyond all these limits.
So what we have here is actual experimental data of a working cloak. This works at microwave frequencies.
This region here is what you're cloaking?
So this region inside is the cloak, what would be cloaked, and this out here is the cloaking material. This is a truly invisible device. It's not just transparent like a piece of glass, where you can see that there's a piece of glass there because it distorts the scene behind it. This actually perfectly reconstructs everything.
The Duke group did a very important experiment when they verified these ideas using microwaves, long waves. It proved that the concept of cloaking, the concept of metamaterials, the transformation that was used to make the light go around, it proved all those things were correct. But its limitation is that it was at one specific wavelength and not a visible wavelength. So there's 1,000 challenges in bringing that up to the visible. One of the most advanced concepts is the conformal cloak. And that's like a blanket. That's something that you could put around any object. Now the thing about a tank is it doesn't change shape too much. Turret moves and so forth, but there you know the shape, and then you could design a conformal cloak that fits right on the metal and render it invisible. Anything that fits around a person or an object, so a shirt, it could be the uniform, or it could be a blanket they put around themselves. I think the applications are widespread. It's just that we're not ready to build things like that yet. They're just years off. It's going to be a while before soldiers have cloaking devices, but that's the ultimate goal.
Imagine if we took, all the small arms projectiles that the Army uses now, and we hand one small arm projectile to the soldier, okay, with one weapon system. Just imagine what that would do for the Army if we could do that.
And imagine a projectile 10 to 20 times more powerful than anything used by today's soldier. To get that bigger bang, Army researchers are trying to develop a new kind of explosive, using what they call disruptive energetic materials.
Currently, we're exploring materials that you normally would not consider to be explosives, such as nitrogen or hydrogen or carbon monoxide. These are materials that we're planning on putting in the Army capabilities within 15 to 20 years, so far-term research.
They're testing the use of lasers as a possible way to trigger the awesome explosive potential of these exotic materials.
We're also working on materials that have what we call dial yield performance. That is, the soldier himself could decide what type of performance level he wants out on the field, where you could have one explosive doing the job that we have several explosives doing right now.
The soldier would be able to control that effect in the future. You could potentially use that round against an armored vehicle to destroy it. Take it to the far extreme, we could also have non-lethal capability into that round by just understanding and controlling those materials. This is a whole new class of materials that if we do it correctly, it's a game changer.
So one of our other challenges is being able to hit the target every time. That's our future vision. Every time the soldier pulls the trigger, he hits the target. So our focus is developing the technologies that will allow those precision-guided munitions to be produced at a very affordable cost. For the shoulder launch systems, we're looking at literally shrinking the capability that you would get out of a tank or an artillery round today into something that a soldier could launch from his shoulder. Another huge challenge for us is engaging targets in urban environments between buildings. So a system like this would allow him to shape that trajectory to fly up and over and actually come back into the reverse side and then tailor the effect, the warhead effect itself.
Full spectrum capability in the hands of the individual soldier. Tank-like lethality. So one round that would replace many, many rounds is where we see the future of lethality going.
How can we utilize brain signals to actually directly control our interactions with a computing system.
Soldiers of the future will also be more connected, sharing vital information with their unit and other sources, using powerful electronic tools to get the right data at the right time.
You have to limit the information to what the soldier needs to function. Situational awareness will be coming to him from sensors. He has to have his own sensors.
Just getting into a good position, over.
We've got to make sure not only soldiers can talk to each other by voice comms and by messaging. On top of that, you've got to communicate with all the different sensors on the battlefield. This includes everything from the unmanned aerial vehicle to unmanned ground vehicle, so something you might kick out into a building before you enter. If you're carrying something like the any kind of ground soldier system, hopefully we can get that down to a smartphone. Like when you want soldiers A and B to go to place C, like, you know, just go up to them and grab them and shove them over there. Well, that's the team leader's technique, right? When a platoon leader wants somebody to go somewhere, he can drive what's called a chem light on the screen. That tells them instantly where to go. So when a platoon leader wants two squads to maneuver, you know, kind of around building X and the other one to come up to the front of building X. So with the screen, hopefully, it'll just be able to say, you here, you there.
You give him the information that he needs in terms of where he has to go, who is with him, how, you know, what you should look out for on this road, what's the experience. You would be able to sense infrared, sense invisible, have a receiver for your radar. You could put the optic, slide the optic off of your helmet, and the optic would tell you there is an unknown at 800 meters to your front, moving from left to right. So he could see the target, he could gain instant advantage in terms of situational awareness. He's got all the information he needs in a very compact form, either on his wrist, on an optic that comes across his face. Those are the kinds of things that would make his job much easier.
For the most part, our target audience, it really is the individual soldier. That typically is, again, looking at developing the beginning stages of technology that is, for the most part, going to be used by the soldier on the ground. You can have applications that enable you to plan new routes in a more efficient manner. Ways in which you can display information coming from a forward operating base in a more efficient fashion. Or custom tailoring displays and custom tailoring technologies to the individual roles within a squad. So instead of everybody getting everything, then you have the right information in the hands of the right people at the right time. And all of that kind of builds together to make the soldier more efficient. As a result, we're looking at the brain and the body in the context of the mission. So we are really concerned with the soldier and their environment.
And researchers are exploring the use of sensors to tap a soldier's brain power as a way to monitor and even improve their performance.
These systems, by their nature, have to be located on the head, which means they have to be located under a helmet. When a soldier is subject to a blast or is subject to a ballistic event, a bullet that hits them in the head, well, those pieces of metal that would be inside of a helmet then become secondary projectiles. So any type of design that is dependent upon metallic sensors probably not going to be able to be deployed in helmet, in battlefield types of situations. So some of the things that we've been working on are foam-based sensors. So sensors that use conductive fabrics and conductive foams that can actually be part of the protective element of the system, and then they could actually be integrated with the foam padding of the helmet. It's critical for us to get the best sort of measurements that we can. So some of the sensor work that we're doing right now is really aimed at getting those measurement capabilities to a point where we can actually really use them in the real world as our soldiers are moving through urban operations, moving through across cross-country terrain. And sometimes we can pull off signals from the brain that are that signify when when a person has, for example, identified a target and may not even be conscious that they have.
The future soldier might even have the ability to control a computer device through a direct link to the brain, hands-free.
One of the more straightforward applications that we can think of is how can we utilize brain signals to actually directly control our interactions with the computing system. The approach of brain-computer interaction technologies is to design systems that function naturally with the way in which soldiers' brains function, to effectively perceive and process information. When you actually do these types of brain-computer interaction interfaces, trying to take away the burden of manual interaction with the computer system, well, it's actually quite effortful. So some of the things that we can do in the laboratory, obviously they take some time.
Army researchers are also focusing on new ways to keep the future soldiers' high-tech gear powered up and ready.
You think about the soldier, people are thinking about the soldier, what power requirements he has. You think about there's computing, there's communications, and there's displays. And I think all those arenas there's potential for reduced energy demand. We're trying to get to a 5-volt battery. That would potentially extend the capability of the battery by roughly 30%. Translate to soldier, roughly 1/3 less batteries you'd have to carry, or 3 times mission duration for the same battery.
A lot of our stuff right now on a sort of standard soldier gets powered by its own battery, but not all of it, not like all of the communications, for example. How do we go ahead and try to integrate all of those power sources, maybe into one common power source, or do some kind of breakout of some powered by each individual battery and some powered by a central power source? And what are the problems if we think even bigger than that and say, how do we power a mission? And how do we get a small combat unit or tactical small unit? How do you distribute power among that squad? And how do you distribute parts of a power generator or something among that squad? You're losing some individual capability.
The Army is putting together a doctrine called operational energy. And part of the doctrine says, hey, I want to be able to use energy more efficiently, reduce reliance on fuel and recharging and battery resupply. So I want to be able to produce and use energy locally wherever possible. So, this is where some of the alternatives come in. And then we're looking at some alternatives besides batteries. We're working here on fuel cells and some fuel cells that may be able to use a variety of different fuels.
Even more sort of further out there might be developing wireless technology so that within a radius of whatever number of miles we need, everything in that radius will be powered without you having to do anything or carry anything.
If I take a stick here and very slowly go in and out of the fluid, I can kind of go in and out, but if I jam it in there, I can't penetrate into the fluid.
One of the things we realize is that the soldier is not a person who can carry any weight you want to put on his back. A person has limits in terms of his endurance.
Our job is to really increase the capabilities for the soldier, but reduce the weight at the same time.
From the science and technology point of view, it's a total ground-up development effort at headgear design. Lighter, stronger, more integrated. We want a streamlined solution that commanders can up armor or de-armor their soldiers depending on the mission. Lightweight materials that are not going to induce near or short-term injuries to the neck and back. Lighter materials for improved mission performance, and just the overall streamlined system. We're looking at the balance and the center of gravity of the helmet from the biomechanical point of view. And then to go along with that, we're taking a look at the weight of the helmet, obviously, to reduce soldiers' load. We're investigating some new heads-up display technologies, more particularly see-through heads-up display. You have that micro display, it's a solid piece of equipment and it reduces your field of view. So we're looking at technologies that will help open up that field of view and give the soldier more peripheral vision. Soldiers are experiencing a lot of wounds to the face due to secondary blast odor effects, whether it be glass, rocks. The different communities are looking for some sort of lower face protection that they can add on if they want to. If you want to be able to protect against every single threat that's out there, you're going to have a 10-pound helmet, which is not going to be good for the soldier. Not only for their situational awareness, but the short term, they're being able to accomplish their mission. Long term, possibly long-term disability or injuries.
The idea is that we're always on the hunt for new materials that are going to give us a decisive advantage. The future helmet technology here we see largely in exploring new materials to address what we consider new issues. Rifle protection, blast resistance. Historically, helmets have been designed for ballistic resistance. They have not been designed for blast. But as you know, it's an increasing concern, like what's the impact of blast on the soldier? And that's what we're exploring now, is how do we reduce the incoming impulse to the helmet and actually ultimately to the brain.
What we find is the enemy picks the areas where we're most weak. And one of the areas that we're weak is the protection of an individual soldier.
We have armor that we put on our soldiers right now that are rigid and stiff, not very comfortable for them to wear. We'd rather have all flexible, conformable armor. There's always a desire to engineer conformal, flexible, comfortable armor. And any additional tools we can come up with to help in that pursuit is going to be beneficial. A shear thickening fluid means you have very small particles dispersed in a liquid. So these are very small, very hard, smooth, spherical particles. And what's really interesting about this is this, by volume, is over 50% solids. So over 50% of this is solid glass. If I take a stick here and very slowly go in and out of the fluid, I can kind of go in and out. But if I jam it in there, I can't penetrate into the fluid. We saw this material, saw this as an opportunity to perhaps exploit it for military application. Our body armor that we wear right now is composed of fabrics like this. It's a plain woven Kevlar fabric, great ballistic protection. Now if I take the same fabric and I add the shear thickening fluid to it, it kind of acts like a glue that kind of holds together the yarns and fibers, does not permit them to slide past each other. So when I engage it with the awl, its only option for getting through is to break Kevlar. It's not going to let things slide out of the way, and you're just not strong enough to break Kevlar by hand with a tool. So I get that great puncture protection with something that's still nice and flexible. The heavy lifting is still done by the fabric. You need a high performance fabric in there. This is just altering the way the fabric is interacting with the thread. You're not going to see the fabric disappear and be replaced by purely fluid. It's because we're taking ballistic fabrics and treating them to give them puncture resistance. We can actually make a body armor material that has both puncture resistance and ballistic resistance. This technology primarily is addressing the soft part of the armor. So potentially, if it's designed properly, we could look at reducing the weight or the thickness of the vest. And because of the unique properties of this material, it gives us a lot of opportunities to really tune performance and potentially get us into doing things like creating extremities protection for the arms, the legs, the groin. This is basic research at this point, 5, 10, 15 years. And in fact, as we continue to learn more about the material, we might discover a completely new direction that will lead us down a different path.
And soldiers are playing a key role along that pathway by providing a unique blend of feedback on behalf of the future soldier.
An HRV is a human resource volunteer. We go and recruit these soldiers out of their schoolhouse, and we just tell them what we are about. Tell them that they can come here and just be volunteers for certain programs that we have. Typical cycle, we can have anywhere from 25 to 33 volunteers, depending on how many studies are going on. They're each here for approximately 90 days each.
The first time we went in, they brought us to 5,000 feet, back down, and then they brought us up to 11,500 feet. And then we sat in there for a good half an hour just to see if everybody was okay with it, no one was getting sick or altitude sickness. They put a tube in your mouth, and then they tell you to breathe, and then breathe in heavily, breathe out heavily, in and out. When they first came, they started talking about how this is going to help people on deployments and everything, and I thought it'd be really beneficial to my brothers and sisters in arms that, you know, we could help them out in the future.
We're really just beginning to understand the relationships, all the intermingling relationships between the brain and the body and the environment. The nice part about virtual environments, immersive virtual environments, is you can control every aspect of the environment. You as the experimenter know exactly what variables you're manipulating, but at the same time creating a very realistic, immersive, again, sense to the soldier.
Enemy down. All right, moving into the building.
We could measure a soldier's ability to walk toward or away from targets. We could measure how quickly they respond to situations, or how quickly they make decisions between potential targets. So we can use these data to construct kind of models of soldier performance.
Enemy down.
So a piece of technology can have a load associated with it if it distracts you, if it requires your attention periodically. The goal, of course, is to have it complement the soldier in a natural way.
It all comes down to capabilities. It all comes down to requirements. It all comes down to what does the soldier need on the battlefield and what makes sense.
What we like to do is we like to lay out the long-term vision. But when we see the golden nugget, the potential game changer, we introduce that much quicker into the force. I like to think imagine.
And right now we're what if in many other fields too. So that's a very important part of what we do. And then of course you have to back it up by reality. And sometimes, you know, reality is just a blade of a guillotine, cutting your idea the head right off it. But every once in a while the ideas work out.